All right, welcome everybody. Can't say I didn't do anything nice for you. Uh, this could be considered your charitable gift, so never can it be said that I didn't do anything nice for you. Um, it's a very important day today. It's a very good day. Um, Probably most of you won't realize exactly the true depth of how actually important today is, but we'll leave that there. I'm going to do a quick review of some of the top level concepts. Um, and I'm just going to leave it in this screen mode so that we can kind of quickly flip through the key concepts. 9, 10, 11 have a lot of material in them. There's a lot of detail, a lot of things that we've got to pay attention to. So what we want to do is we want to walk through the fundamentals of all of these composition related changes, the phase equilibrium, the phase diagrams, and what that has to do with everything leading up to chapter 11. So let's get started. These are the topics that the exam is going to cover, so I'll highlight the things that I think you need to really pay attention to. Really, it's all of it, but we'll go back through some of the key details here. So the phase diagrams, there are a lot of specific details. We want to pay particular careful attention to the difference between solutions and mixtures, and we have a lot of different aspects of our solubility limits that come into play. So mixtures are more than one phase, multiphasic by nature. They are also helpful for a lot of details. So we have the solubility limit 220C, and we have a couple different things that we're going to focus on here. All the interruptions today. Okay, so we're talking about the solubility limit, and we have an example of a sugar water phase diagram. How much can be absorbed at a given set of conditions? It's dependent on the temperature, and then the composition will change. There will be a line across which there is a limit of solubility, how much can be dissolved, and that's very, very important. So you'll have multiple phases, often in these crystals, in these metals, and we have a bunch of the key aspects of the behaviors of materials wrapped up in how these phases are coupled together. So in the case of the syrup, so liquid, i.e. syrup, solids, you start out at 70% and you go all the way up to about 85 or 90%, but only above the saturation or above the solubility limit, and how that interacts. So you start at a 70% concentration. As you heat it, you cross the phase boundary again, so it becomes all liquid. Then as you add more of the sugar, so increase the weight composition, you end up crossing the phase boundary again at that elevated temperature until all the sugar can't continue to be dissolved. So you reach a boiling point, so there's nothing above this range except you get into steam and other things in the phase diagram. Then you have these paths that we take across. We're going to carry that concept through to this. So the criteria for solubility, this is very important to understand, is they need to be similar in electronegativity, and they need to be similar in atomic radius. The more similar they are, the more easily they will be able to, based on the Hume-Rothery rules, which is what these are, they, especially if it's the same crystalline structure, So similar electronegativities, similar radii, Hume-Roth 3 rules. The nickel and copper are soluble in one another for all proportions, meaning in all conditions they will be similar. So looking at the copper nickel phase diagram, from 0 to 100%, this is a fairly unique phase diagram among metals because a lot of them aren't like this for bimetallic alloys. The temperature and concentration, the weight percent, and the phase matters. So the liquidus line, solidus line are important for understanding how things cross these boundaries. You have the solid down below at lower temperatures, so lower being relative, because they're talking 1100 C is the lowest melting point of either of these, so it has to be at least 1100 C. Below that you have a solid solution with face-centered cubic. Above that, depending on where you are in composition, it's a much higher temperature. The pure nickel has a high melting temperature, much higher than pure copper. And what you have in between is this phase envelope that has a curve, because certain compositions have a much higher melting point than either of the pure, or a much higher melting point than the pure copper. So the solution starts to change its phase behavior. And we have the liquid, the alpha, and the liquid plus alpha region. So liquid plus solid. We've seen a lot of examples of those when the crystals form in casting. It's very easy to see the crystals form. You guys have seen a lot of examples of that from the stuff that I've pulled together to help visualize some of this. So we've spent a lot of time on this. It's probably important to go back and review those specific lessons, because you're not going to get a single recap and everything you need to pass the test in this one lesson. That's just not reasonable. So if that's your expectation, you need to change your expectation. Copper nickel system, binary meaning two component, isomorphous meaning completely soluble of one component in another, rather than polymorphous, which is most alloys. There's certain amounts that are different in terms of solubility, but copper nickel happens to work together really well. So it gives us an ideal case to study the principles. So at a set of conditions, you are given coordinates, and you need to be able to determine what the phases are on a phase diagram. So for 35 weight percent for this first case, at 1250 C, we're in the envelope with liquid plus alpha. So that's the composition is two phase liquid plus alpha. For the second set of conditions at 1100 C and 60% nickel, you have one phase and it's alpha, only the solid. So that's what we do. Yeah. So we have another couple compositions here for the same starting composition. Depending on the temperature, we use these tie lines for phase diagrams. So many students get really super confused about this, but it's really important to understand. So as you start at D, somewhere around 1190 C, as you heat up this 35% composition into the liquid plus alpha region, the two metals melt differently because they have different melting temperatures individually. So you shouldn't expect them to just have one melting temperature. You should expect the composition to be different. So there should be more copper melting rather than the nickel, because the nickel, the pure nickel, has a much higher melting temperature. So less of the nickel should melt, more of the copper should melt. So there should be a different composition based on that. So when you mix the two together, one is melting faster than the other one, out of solution, so the concentrations change. So this isn't actually confusing. It actually makes sense. So at B, we draw a line across to the liquidus line, another line across to the solidus line. These are tie lines that tie us back to the phase envelope. So the liquid composition is 32% nickel, while the solid is richer in nickel, being 43%, and that's what we should expect to see. So we draw our one line, tie line to the liquidus side. Liquid composition is 32%. Our other line draws across to the solidus line, and that tie line tells us we're about 43%. This is an estimation based on the fundamentals of ruler reading, which I assume you guys can grasp. It's helpful to use rulers and straight edges and things to get the best approximation that you can, especially when you're doing it on a digital screen, which unfortunately is what it is. So I'm not going to bust you back to private over 31 versus 33, as long as it's clear you're not telling me 57% and 22% with your tie lines. I will give you most of the credit for this because it's clear that you have paid attention and understand what those are trying to do. So you do have to do some estimation. Yeah. So for the third kind of key concept, if we know the temperature and composition, we can determine the weight fraction based on this data. So starting at 35, we heat to this temperature. We know the phases are both liquid and solid. We can determine the composition of the liquid at 32% and the composition of the solid at 43%. So that makes sense. And from that, we calculate using our liquid side. So the left side is the opposite over the sum. The alpha, the solid side, the right side, is the opposite over the sum. And that's just a thing that you need to remember which side is which. So we get a liquid composition of 73% and a solid composition of 27%. So it should be mostly melted if it's this close to this liquid line. If it's closest to the solid line, we would expect it to mostly be solid. That's how you tell whether these numbers are correct or whether you might have them backwards. It's really close to the solid line, should be mostly solid. Or if it's really close to the solid line down here, it should be mostly solid. If it's really close to the liquid line, it should be mostly liquid. That's your sanity check for these processes. So when we're working with these lever lines and tie lines and things, we want to make sure that all of these are carefully calculated, so they're an estimation. And again, your weight fractions, the way that you calculated them, are 75%, 25%. You're in the right ballpark. If your weight fractions for the liquid are 27% or 25% and 75% in the solid, you will be wrong because you did it backwards. You didn't understand what was going on. You didn't grasp the concept. So we'll talk more about the way that this lever rule works and how to think about it so that it stays in balance. So this lever rule is referred to, it's also an isotherm because it's looking at a single given temperature at different compositions that exist in equilibrium. So the weight fraction for the liquid can be calculated this way. The weight fraction for alpha can be calculated this way. So I think we've hammered that point sufficiently. This is a visual representation of what's happening with the grains. Really, this doesn't cover 100% of all specific scenarios, but in this case, with just two materials, you have a liquid and you have a solid blue phase forming. This isn't like one thing or two things, but the important part is you start out at liquid. At the liquidus line, you start getting some grain formation that's at the same composition that is the original composition of the material, and then the solid that starts to precipitate is the heavier, higher melting temperature nickel, so mostly 46%. As that cools, more of the copper condenses from the liquid phase, just like water does into ice as it cools. More of the copper condenses into solid. So 43% is now the nickel composition in the solid. So the nickel composition goes down as you go all the way down to this range. So it'll reach the same 35% composition. This is just above that solid line, because at the solid line, it's 35%. Just above the solid line, it's 36% nickel and 24%, or 24% nickel is the liquid composition, and 36% nickel is the solid there. So you rapidly approach the ending composition by the time you hit the lower end of the line. So it's really important to understand how all of that interacts, and that fundamental behavior of the phase diagram. So you're going to have different levels of nucleation depending on how fast it's cooled, and that creates differences in the uniformity of that composition. So we talked about that, the effects that this has on tensile strength and ductility, or percent elongation. So these are always going to be inverse in the way the alloys work. So the highest tensile strength is also going to be the least ductile. The lowest tensile strength is going to be the most ductile. That's the way it works. Another example of a binary system, but where you can have multiple different phases, so 3 different phases. So one that has a eutectic point. This is called a eutectic system, because it will have a lowest phase composition where it will be a liquid, and above that is, or below that is, also a higher melting temperature. So eutectic is that lowest point. And we talked about the hypoeutectic and hypereutectic materials. So that allows for a number of different things. Primarily, the low energy input is attractive for manufacturing expense. And that's part of the reason. It's not because it's the strongest or the weakest. It just means it's easier to cast at this lowest combination, this eutectic composition and melting temperature. So 779 and 71.9% silver in this copper silver system. So alpha phase is mostly copper, beta phase is mostly silver. Then you have the liquid phase, you have liquid plus alpha and liquid plus beta. And then below you have the solid, which is alpha and beta together, varied in ratio. So there's no liquid below the eutectic temperature for any reason. And the CE is the composition at that temperature, the eutectic temperature. So this is an example of the eutectic reaction. It goes back and forth between 8% silver and 91% 91% silver from the 71.9%. So there's equilibrium of both of those. As you lower the temperature and you do your tie lines to these features, so we bring it down to 150, you see that at 150, rule number 1 is the phases are A and B only, alpha and beta only. Rule 2 that we can find out information about are the compositions. So about 11% alpha, 99% beta compositions, and the weight fractions we can determine. So again, The weight fraction for alpha is the opposite side over the sum, giving us 67%. So this is lower in composition, so we should expect it to be heavier in alpha than in beta based on what the composition is. So 40% is closer to 0 than it is to 100, so we should expect it to be mostly alpha, some beta. So that passes our sanity check. As we go up at 40% in temperature, so we take that same sample, bring it up to 220, now we have liquid and alpha together. We have no more beta that's formed in this composition. So alpha and liquid only. Alpha at 17% based on our tie line, solid at 46% based on our timeline, based on our tie line there. So the weight fraction for alpha is 0.21. Weight fraction for liquid is 0.79. So we have some interesting things that we can determine there. So we would expect, based on how close it is to the liquid line versus the solid line, that it should be mostly solid, or mostly liquid rather, and low solid content. So that passes our sanity check. Microstructurally, we have alpha. As we go up, we get liquid and alpha together. Then we go up farther in temperature to liquid only. So this is part of what we got to pay attention to at a higher composition. We have alpha with some small beta grains. We have alpha only, then we have liquid and alpha, then we have liquid. And we get this sort of zebra stripy pattern similar to the perlite that we learn about in steel later. So it's these layers of alpha and beta, and importantly, the diffusion that happens preferentially uses stripes like this in order to describe what our patterns look like. All right, so we gotta keep cranking on this. Hypereutectic is above the eutectic point. Hypoeutectic is below the eutectic point. So hypoeutectic has more alpha in this case. Hypereutectic has more beta granules in this case. Then we get into more complex versions of phase diagrams and intermetallic compounds and some of those. The key definitions here, important to understand these. Liquid transformation to two solid phases. One solid phase transforms to another solid phase is eutectoid. So eutectic is liquid to two solids. Eutectoid is one solid to two solids. Peritectic is liquid and one solid to a second solid phase. So this is a little bit harder to identify, but we see some examples. So we have a peritectic point here where we have liquid and one solid turn into liquid and a different solid. That's a peritectic point. Eutectic is two different kinds of solids becoming a different kind of solid. So the iron carbon gets much more complicated, and there's a lot to this. So again, that's a lesson worth going back to review in great detail, talking about perlite. So you have both a eutectic point and a eutectoid point. Above the eutectoid point, you have just austenite. So a lot of steel processing and manufacturing happens in this box here. So usually at or above the eutectoid point for at least what are considered to be higher carbon alloys. Above that significantly gets into the cast iron region. So 3 to like 4.5 or so is that cast iron region, because the eutectic point becomes that lowest melting point and makes casting most cost effective. So with this alpha and iron carbide, you have perlite formed. Perlite is this zebra stripy grain structure. It's a lot harder than just the pure alpha iron, which is a lot softer. So hypoeutectoid steel is below this eutectoid point that has perlite and some alpha iron. Hypo eutectoid, or hyper eutectoid, which is above the eutectoid, is in this uh, range. So yeah, there's a lot of examples of these. So a little higher carbon, a little different behavior from this. They have a lot more carbide sort of phase. So this is the cementite or the iron carbide, and there is, for this hypereutectoid, you can calculate the weight fraction. So again, go back and review that very carefully. For 99% iron, 0.4 weight percent carbon, transform. All right, so for our 0.4 weight percent carbon, we need to know what is the composition, what is the amount of cementite or iron carbide in the 100 grams, and then what is the amount of perlite and proeutectoid ferrite alpha in the 100 grams. So we set up the RS tie lines. We're just below the eutectoid temperature. So we do our calculations, we get our weight fraction. We get about 0.22%, 0.022% in the alpha phase, 6.7% in the of the iron carbide or the cementite. We do the weight fraction for the iron carbide. We would expect it to be very low because we're very far away from that side. So 0.057, multiply that into a 100 gram sample, and it's 5.7 grams. So pretty straightforward example. And we have 0.4 weight percent, 0.022 weight percent in the alpha. So the perlite is the remainder, which comes out to, or perlite is just above this temperature. We can calculate this. So we're in the same weight fraction for the original composition, but the new weight fraction drawn down from this point is at the eutectoid concentration of 0.76 weight percent carbon, just above that position. So the perlite that forms is consistent with this 0.512. So multiplied into 100 grams, that's 51.2 grams. And other alloying elements, we talked about quite a bit about this. We have the eutectoid temperature increases significantly with these additives, decreases with these additives for the alloys, and then the eutectoid concentration shifts also based on these additives with the weight percent. So significant change in percentage with titanium, a lot less so with nickel. Nickel's a lot more gradual. So the other stuff is kind of in between. The next detail is about these phase transitions and what some of this is. So nucleation, the start of crystal growth from a single crystallization, small supercooling, slow growth, large crystals. Large supercooling, so big temperature rate change, many nuclei, lots of small crystals. Homogeneous or heterogeneous nucleation, heterogeneous being there's a something like at the mold wall or impurities in a liquid phase. We talked a lot about some examples of what that looks like practically. There's a threshold, a critical radius for nucleation where the Gibbs energy, the change in Gibbs energy is maximized. That's the total free energy here that's maximized. That's what this curve is. So the volume free energy versus surface free energy. As that radius increases, surface free energy increases. Also, the volume free energy increases or decreases rather. volume free energy decreases. The solidification happens as a function of these radii. So the solidification process can be described in terms of the latent heat of solidification and the degree of supercooling, i.e. the delta T. The kinetics, meaning how fast that reaction takes place, is temperature dependent. That can be monitored through things like X-ray measurements. We have a description of the slope of growth. It's taken to be the half time where 50% of the fraction has been transformed. For the simple, basic, fundamental kinetic equation, by convention, rate is 1 over T half, meaning 1 over the half time. On this graph. So increasing the temperature greatly decreases the time for transformation. And it makes sense from the standpoint of more kinetic energy has more a greater ability for rearrangement of the atoms. So at low temperatures, the diffusion basically can't happen very quickly, and it takes forever to get a transformation from one type of phase to another. The eutectoid transition here is we're able to undercool below that temperature, and we can see what our composition looks like. So gamma goes to alpha and iron carbide, so 0.76 weight percent from the eutectoid point down to 0.022 weight percent in alpha and 6.7 weight percent in the iron carbide. The diffusion happens such that it preferentially, the carbon gathers near the iron carbide area, the cementite, and the alpha regions are lower levels of diffusion for the carbon. At the higher temperatures, you get more perlite over time, but at the lower temperature, meaning the greater the delta T, this is the delta T itself, not the absolute temperature. So if the delta T is larger, the faster it cools because of the larger delta T, the higher percentage of perlite you're going to form based on that phase transition principle that we covered here. So what does that look like? At a given temperature, at the eutectic temperature, you cross through into perlite and you get a certain composition. If you cool that below that temperature, you get a different kind of composition and a different grain structure. As you transition through these temperature regions, especially if you cool it down below this 500 range, you get down into the bainite region instead of perlite, which is like perlite but shorter cementite grains. Then you can get spheroidizing if it's left for a long time to equilibrate, often at temperature for some 24 to 48 hours. So if you cool very rapidly, you force the metal to go from FCC to BCT, body-centered tetragonal, and there's a lot of sites for the carbon, and it forms these sharp shards, which gives us a very hard cutting edge. So it's very brittle, very hard. There's very few slip planes, so it's very durable. So it's a lot of lack of ability to propagate faults, meaning it's more durable. It's a better cutting edge. So this is why there's a big difference between stamped steel knives for inexpensive knives and handmade forged knives that are many hundreds of dollars. Even though both are fundamentally made to cut things, one is going to have a very high degree of martensite, the other is not. So they're going to be very different in terms of durability and use. So we do have some martensite. We do have a diffusionless transformation for martensite to happen. That sort of locks the carbon into place. Adding some of these alloying elements changes the phase transformation. And a continuous cooling curve might look something like this, where it transitions through austenite to pearlite. And then mostly you'll end up with pearlite and very little martensite. But if we look at some specific examples, so they give us a few different variations. 42% pro-eutectoid and 58% coarse pearlite. To get there, we would have to isothermally treat at 680C and then cool precipitously below that point. In order to get a 50-50 mix of perlite and bainite, you have to quickly cool, ride the line at 600 between bainite and perlite so that both have a chance to form equally, then drop it down below the 500 mark at 470 so that all remaining austenite turns into bainite. So you get austenite and bainite, and it all transforms into bainite, and then you cool the rest of the way. So for 100% martensite, you rapidly cool it all the way down to room temperature about. The 50-50 martensite, you cool rapidly to 290 and hold it there in order to form a different version. So there is going to be a mixture of these two. Hypo-eutectoid below the eutectoid point, there's going to be a lot of alpha, a little bit of perlite. Above hyper-eutectoid, it's going to be a lot of perlite, a little bit of cementite in the main phase. So tensile strength goes up with weight percent carbon, and the ductility decreases, so things that we would expect to see. Mechanical properties are, again, inversely related between the hardness and the ductility. Spheroidized is the weakest in terms of hardness, so it's the weakest. It is the greatest in terms of ductility, so percent retention of area, or percent reduction of area rather. So it's the most compliant version of steel. The hardness of martensite is greater significantly, many times more than fine pearlite. Fine pearlite is a lot harder than alpha iron. So that's why we use those to make cutting edges, because that hardened material works really well. As you heat treat and temper something, you decrease its tensile strength, you decrease its yield strength, increase its ductility to make it easier to machine, for instance, or easier to form, easier to stamp, etc., easier to conduct processes. So from austenite, where a lot of steel spends a lot of time in processing, slow cooling gives you perlite, moderate cooling gives you bainite, rapid quenching gives you martensite, and then some tempering will give you back some of the perlite and bainite, as well as tempered martensite. So that's the strongest is martensite, also the hardest, and least ductile. Spheroidite is at the other end, so it's the softest, least strong, and most ductile. For 11, we're kind of talking about the blocks of different groups of materials. So steel's below about 1.4 weight percent carbon. So most of them are in the 0.1 to 0.5 or so. A lot of them high carbon steels for tooling and things are up here in the upper range. Cast irons 3 to about 4.5% carbon, and that includes this eutectic point where cast irons are cheapest to manufacture because of the lowest temperatures. So we talked a little bit about, and this is another good lesson to go back and review in careful detail, increasing strength, costs, decreasing ductility. So a normal 1010 steel is not hardenable, doesn't have enough carbon. You can heat treat it, but it doesn't change the properties. They are exactly the same. Some of these alloys you can treat, at least to some extent. And then you have 4340 is highly heat treatable, 1095, 4190 are extremely heat treatable, very hardenable because of the higher carbon content, lots of opportunity to form martensite. That works really great for drills, saws, dies, all of those sorts of things. So the refinement from steel ore, they add in iron ore, limestone, and coke, so that they get CO2 generated. You have reduction of iron ore to metal, CO2 and carbon to form 2 carbon monoxide. That combines with the iron oxide in the ore to become iron and carbon dioxide. The limestone, calcium carbonate, combines after splitting to calcium oxide and CO2 at high temperature to come in with silica and alumina to turn into slag. So that comes off the process and you get molten iron at the base. So all of these have naming schemes. Plain carbons are 10. Plain carbons resulfurized are 11 for better machinability. The 15 series is manganese from 1 to 1.65. 40 series is molybdenum. 43 series is nickel, chrome, molybdenum. Very common combination of materials that impart a little bit of corrosion resistance, but a lot of strength, higher melting temperatures, much tougher overall alloy, especially when forged. The 44 series is 0.5% molybdenum, so a lot higher percentage. The 2X's are the weight percent carbon times 100, so 1060 steel's 0.6 weight percent carbon, so that should make sense. Above 2.1 weight percent carbon is cast irons, so more commonly in the 3 to 4.5 range. Low melting point, brittle but hard, works really well for those applications. It's typically a slow process. There is also graphite at the far end of this phase diagram. There's a bunch of other stuff in between, but we're not going to get into that for a lot of reasons. So the types of cast iron: gray iron has flakes of graphite, ductile iron has nodules. They sometimes have magnesium or beryllium. So it's a perlite-like matrix that's stronger but less ductile. White iron is a little bit less common, so perlite and cementite, very hard and very brittle, so it's not as practically usable as some other things. Malleable iron is heat-treated white iron at 800 to 900, forming these rosettes. And compacted graphite iron, good resistance to thermal shock, high thermal conductivity, lower oxidation at elevated temperatures. That's your cookware grade of cast iron that you guys saw the examples of. And that lets us get a pretty good handle on what's going on for these. So you have a couple different processes that they use. The first is a reheat and hold at 700 C for 30 hours. A fast cool gets you malleable perlite. Slow cool gets you ferritic malleable material. White cast iron, so as you go up in the range, fast cool gives you white cast iron, moderate cool gives you gray cast iron, slow cool gives you ferritic gray cast iron. The higher carbon content with magnesium and ceruleum gives you perlite ductile cast iron, and slow cool gives you ferritic ductile cast iron. So yeah, that gives us at least a range of what those applications would be. So the ferrous alloys are high densities, meaning they're heavy. They are low electrical conductivity, so they're not really good for electronics. And they have poor corrosion resistance because that's just the nature of the material. So non-ferrous alloys, copper, aluminum, titanium, bronze, magnesium, refractories, nobles, all of these are non-iron containing, and they all have their own purposes, their own end applications, their own unique properties, such as titanium being almost as strong as a stainless steel, typically, but much lighter, almost half the density. Aluminum is almost a third of the density. It's a little more than that. It's like 40% or so. So it gives a pretty good option for making high strength alloys. Hot working versus cold working, we spent a bunch of time thinking about, especially in terms of forming. So dyes and forging, drawing, extrusion, rolling, both hot and cold. We've seen examples of all those. Casting, we've seen examples of those now, several. Where you fill the mold with a molten metal. The mold is made of a compacted sand. So sand casting is the most common because of its low expense. Makes sense. There's investment casting, meaning you start with a wax or something else, you melt it out in a form, and then you add the molten metal to it. There can also be die casting, where you add the molten metal into a die and form it. Then there's continuous casting for like rectangular slabs or cylinders that can work. So you have molten material and then you have solidified material that comes out the end. There are some applications where that's kind of like an extrusion, but at lower expense. So there's some instances where you would want something like that. So powder metallurgy is becoming more common in the industry because of its relative low expense compared to some options. So there's a lot of MEMD parts, or MIMD, metal injection molded. So the powder metallurgy starts with points of contact. As you heat those and compress them, diffusion causes those to form grain boundaries together, and it fuses the part. So metals with low ductilities, meaning they're very brittle, but work in an application where the surface needs to be kind of hard. So we're doing a lot of like oil pumps and oil pump gears and things of that nature that are these kind of fabrication processes. Welding, you guys will do later in the semester, so we've talked about that a bit, joining the types. So there are different types of annealing depending on what your goals are, to relieve the stress, to make it easy to machine, negate the cold working effects, and bring back some of the ductility. A lot of different ways you might want to do that, depending on how you quench it, how quickly, and to what temperature. You have a full annealing, which is very slow cooling. You have a quenching, which is rapid, and then you have a tempering, which is bringing the temperature back up to normalize some of the stresses from quenching. Then the Jominy unquenched test, you heat up the whole rod and then cool it from one end. It gives a differential hardness across the surface. So different levels of hardness as the curves, as these cool differently in different parts of the material. That's why we understand how these differences work and how these different curves look. So the hardenability versus alloy composition. The alloys are going to shift the nose higher typically in terms of time, to give you a little bit more time to be able to quench and an easier time forming martensite, which stands to reason. So the influences of quenching media change. Air is a low speed quench, oil is a medium speed, water is a high speed, and depending on what happens, the cooling rate at the center is always going to be slower than the cooling rate at the edge. The bigger difference there is there, the higher the internal stresses you add to the process. So precipitation hardening means cooling it down and then allowing these precipitates to form. And depending on how quickly you cool, these have different precipitations that can form. So you also can heat treat, then you form precipitate at a lower temperature typically. So you heat treat to get it down to the base, then you bring it back up to a precipitate temperature so that something can start recrystallizing, and then you bring it back down. So when you do this process for something like a 2014 aluminum alloy, when you shift and heat treat, you can change the way the material behaves. You heard the example of aging because of heat treatment that's done, aging the material. That was done for some of the wheels that were being made. That allows for a decrease in the overall tensile strength so that something can be machined again after being much harder. They're aging the material in order to make it easier to machine for some of the last steps, and that's what that curve is telling us about. So there's forming, casting, and then a bunch of other metal fabrication techniques, machining, and all sorts of things. Machining, they can be hardenable by quenching and temperature treatments, but also there can be precipitation hardening, strengthening due to the formation of precipitate particles. And the aluminum and magnesium alloys are precipitation hardenable. So there's all these different factors that we need to consider, but it would be good for you guys to go back and review the other lessons that go into more depth and detail, because this is just a high-level overview to remind you about all of the different things and how they relate together, because all of this all of this comes together to create the end behavior of the material in its application. So hopefully this was helpful. Aside from that, have a great Thanksgiving, and we'll see you for the test.